Okay, today we'll be talking about spread footing. The footing which supports one columns at a time, which is supplied by the vertical load. And the spread footing is a two-way slab, so that we have to place lever in two ways. For example, and you're gonna put the lever this way and lever this way. This is two-way slabs, but with different location of lever at the bottom. Why the bottom? You place the lever in the bottom for foundation. It's simple. You can think of a foundation as a reversely located placed slabs. Okay. For example, you have a slab like this. We have a loading downwards. Okay. And in that case, we put lever at the top. So we have tension at the top. This is very easy. We understood. If you take a look at a foundation, this is the other way around because your now loading is just from the bottom to the top. Upward loading we are experiencing on the slab. So slab tend to deformed this way. It is a sort of a reversed cantilever. So that and and the tension zone is formed at the bottom of the slab where we have to insert or place the bars like that. Can you understand? All right. So the slab slabs and foundations are very similar, except you place the bar in the bottom for foundations because your loading is upward, and you're putting a lever at top sections because your loading is downward. Okay, this is one difference. Actually, there are a couple more differences. We'll talk about that later. Okay, so this is a requirements for placement of levers on foundations. We have to then calculate what soil pressure is acting upwards on the slabs, and that's easy to calculate. You can also think of the soil pressure as a loading, superimposed loads on the slabs. So here, this is a soil pressure. So soil pressure is the pressure which occurs due to the vertical load. So you divide the vertical load, factor vertical load by the area of the foundation, gets you a soil pressure over here. And this is a uniformly distributed soil pressure. You can calculate your moment due to the distributed soil pressure easily, and this is what you have to consider designing a reinforcing for slabs. And we'll take a look at how to calculate those things in later examples. Okay, now the how calculate shear force right now. This is bending. Okay, it is fractional moment. You have to be ready. Okay, and there's another very important loading that is acting on the slab is called shear force. We have two types of shear force, and that is a one-way shear, and the other is a two-way shear. We knew already in slab design, but we're going to review here. Just review those who need some review on one-way shear and two-way shear from slab, please. And there's a one-way shear is assumed to occur at distance d from the face of the rigid surface, in this case column surface. And you have a maybe you are expecting a cracks right there, failure right there. Okay, this is called a failure line. Okay, critical line, critical section, whatever you call, right? And you're acting your soil pressure right there. This soil pressure is gonna cause this section to fail in shear. Okay, but When you take a look at moment will cause a loading from the face of the columns. Okay, they are different. Okay, the acting edge is different. You're talking about the fractional moment. You're calculating. You're considering your bearing pressure, soil pressure acting from the face of the columns. When you consider a shear, especially one-way shear, you're considering a shear from D, distance from the face of the column, and this is your shear force acting on your one-way slabs. Okay, and this formula is universal, isn't it? From slabs, so that in slabs, probably you may consider shear. Actually, you don't consider shear reinforcement in slabs and foundation either, because we don't have enough depth to put shear deformation. It's just vertically placed. So we usually ignore this for foundation design. So we only have these terms left, right? And this is a universal equations for calculating shear capacity. It's a nominal shear capacity, and this is a depth of the foundations, and this is the the length of the critical section, and this value is a should be less than the design shear. Okay, and this is factor shear, and this is nominal shear. Okay, if there is no fifth factor, we call this nominal shear. Okay, if we have fifth factor, we call this a design shear, and this is factor shear. We have three types of terms here. Don't get confused. All right. So we always indicate u here as a u for indicating factored load. It doesn't matter shear or moment, the actual load, all we just indicate with the u, little u over there. And then this is a design shear, and this itself without fee factor is called a nominal shear. All right. Okay. And next, where we have two-way shear right there. Two-way shear is the shear where we are acting the subject the foundation on two ways. Okay, something like this is exactly as punching shear and slabs, and you can say the punching shear and foundation as well. So where what is the critical section for two-way shear? The critical section for two-way shear is d over 2 from the face of columns, right? Yeah. So the instead of taking d in one way shear, we're taking 2 over d over 2. Okay, d over 2. So this is d over 2, and this is d over 2. So we are expecting failure occurs at the section where is d over 2 from the face of columns right there. Okay, and all this outside of the critical section is the area which is subjected to soil pressure. All right, so soil pressure is acting upward on this hatched area to try to punch out your foundation around the column, which is d over 2 away. Okay, understand? And this is nothing new if you recall the design of two-way shear stuff. Okay, and we have three equations as well we saw from slab design. We have three cases here, and we have two cases here. As far as in terms of beta c, the beta c is the ratio of long side over the short side, long side over the short side. Okay, and beta c is when beta c is greater than 2, you use these equations. And when it's beta c is smaller than less than 2, you use this equation. So these two equations never met in one design, as you know. So you can use one of these two, and then you have to use all these. It is the equation which reflects consider your column locations. Okay, so when you column it at corner footing, at the center footing, or edge frame. Okay, so this is 40, the biggest when your column is located at center. Okay, this is so you are taking your nominal capacity or design capacity the biggest when you are locating your foundation under center columns. Okay, so center column is most like provides you with the most favorable design share, which is nominal share. Okay, and you're going edge, you taking 30, you're going to corner, so you are not very happy with this location in terms of your bending and the share nominal share capacity. Okay, this is what you are doing considering the location of column when you determine alpha s. Okay, and here this is and these three equations must be checked, and you take the least value, the smallest value, to define your nominal capacity of the foundations. Okay? And you want to compare this to the which one? Okay, here factored share, right? And if you satisfy these relationships, you're okay. If you're not satisfied this, then you probably go ahead and do something necessary to increase your design capacity here. And this all involves with the economics, right? So maybe you can do some AI analysis to try to determine the best price, best cost, or the worst, avoid the worst cases of cost in your design later, probably. All right. And this is how you design a street footing, a independent footing. Okay. And this is nothing new actually. The one thing, as I said, is different is where you're gonna place your levers in this is bottom, right? Let's don't forget about it, right? But you can just simply think about it. Think about it easy when you flip over the slab like the foundation like a slab. Okay. And now we're gonna take one example before we go into the street foundation. Street foundation is easier than independent foundation, strap foundation, so that it'll be easier when we study spread footing first. Okay. Here we are having some example problems, and we have some loadings right there. We have dead load, live load, and this is service. Okay, we have some property designations here, and we have a footing concrete properties. Concrete footing is less than that of a columns sometimes, 35 and 20, and FY is 420, but right now we're using a 600 megapascal. Okay, it doesn't matter. And one of these important soil property is density. Okay, density. Soil has few densities, and I'll probably have chance to talk about the soil property later. It doesn't matter. You can just study right now. I'm just trying to explain what soil density is. Soil density has a dry density and a saturated density. Okay. And dry density is the lightest one, like 19 kilonewton per cubic meter, right here. So thus the concrete density is 2.4. This concrete itself is 2.0 something. But when you include the rebar weights, all that you don't want to calculate, that's you don't want to have separate calculation of rebars, then you can take a concrete 2.4 kilonewton per cube meters. But the soil is almost heavy as a concrete, which is 19. And when you have saturated, it could be higher than that, right? Of course. Okay. So this is very important property that you want to remember. Okay. And we have a basement loading, and this is kind of surcharge. I told you what surcharges are. Surcharge is loading that acting on ground or acting on basement, whatever, separately from the loading that the soil is supplying. Okay, so you have to consider the surcharge loading, such as basement floor, the loading from basement floor, and allowable bearing soil pressure is also given. You don't have to worry about this value because this value is always provided by the soils engineers. So we pay them and get the report, right? So this particular example, we have a 290 kilonewton per square meter. So it's like a 30 ton, isn't it? 30 ton per square meter. It is pretty good soils, right? 30 ton per square meter. You can support 30 tons per square meter. It's pretty good soil to me. Okay, right? Okay. With all this information, let's try to design this foundation. Okay, so foundation design is exciting because this is where you start your building. Your foundation is not designed well and constructed well, or you don't want to think about the consequences of the completion of entire building. All right, so you should be very careful understanding how to design the building, especially structural engineers are responsible for foundation designing as well. Okay, now let's take a look at, and I told you this is a service load. Okay, and now we have to calculate factor the load from service load given a load factor. Load factor is given per a code, ACI, EC2. So we're following ACI, and we can take a look at EC2 if you want. EC2 is very nice code. So anyway, so this is a factored load. You multiply 1.2 for dead load. You multiply 1.6 for live load. Okay, and we end up with this load which is factored. All right. And this is fee factor where which one we apply to get a design share. This is for fracture and this is for shear. Actually, your fee factor for fracture depends on utility, depend on your strain, reverse strain, right? But just simply you just use 0.9 and the foundation design 0.75 for um, the foundations for shear for fracture. Okay. Then let's go to calculate initial foundation height, size, the area. So as you know, the foundation area can be calculated dividing the vertical loading, and this is a factor when you calculate lever, but this could be service when you calculate load capacity as serviceability, right? So you should be careful of that. And net bearing capacity. And we saw this in last video. So net bearing capacity is a capacity where you have to subtract all the existing load on the foundation, including surcharge. Okay, and this I'm sorry, I'm gonna say vertical loading here. Vertical loading. You can take a look at the McGregor concrete books for this original version. Okay, and now let's take a look at the number. Okay, in problem statements, this is given. What is that? Is allowable bearing capacity, which is given by the soils engineer, and this is the weight of the foundation. So what was the how to calculate? And this is a density of concrete times the thickness. Thickness. Okay? Thickness just initial thickness is assumed. So we don't know. We just assume 0.7 meter. And well, how you assume your thickness of foundations? You can take a look at the column size. So you probably start with a summation of column width 1 and 2, okay, divided by 2. Okay, but this is not a requirement. This is a recommendations. Your column size is what? Column size here the column size is given, isn't it? See, for 15 millimeter, right? So you add this and when you add, you multiply 1 and 2 each. Okay. So you add 450, you add here 450 times 2 divided by 2 is a it's good initial thickness, but not required. You can just 7.8, doesn't matter, right? And this is a soils. You have a soils which is packed on 15 centimeter, right? So if you take a look, okay, now this is a diagrams here. Okay, you have soil the top of here, okay, from ground the top of foundation you have 15 centimeters all packed. So that's another way that you should subtract from allowable bearing capacities right there. And this is a surcharge. This is surcharge, right? Okay. And this is a concrete loading slabs on foundations. So 15 centimeters. This is concrete foundation on basement. And this is a soil packed on top of foundations. And this is surcharge, right? So this is 19 to take care of soil weight, and this is 24 to take care of concrete weight. So this is easy, isn't it? Bookkeeping, just try to follow, not to missing anything, all right? And so your net allowable bearing pressure boils down to this value right there, okay? Boils down to this value. And it gets us to calculate starting initial area of foundations, area of, okay, I recommend that this area of foundation is the foundation that you can modify later anytime. Okay, calculate the total area, and you can assume 3.5 meter. 3.5 meter is this size is subjected to revision anytime later, depending on the calculations. Okay. Okay. Now let's go and calculate loading on the foundation first. All right, on the loading foundation first. And first of all, the most important calculation is this: the net soil pressure. Net soil pressure is different from allowable soil pressure. Net soil pressure is this is loading. This is U, sub U kind of stuff, right? So soil pressure, I could say PU, whatever. Okay. Yeah, somebody can tell me why I do this poorly? PU is a soil pressure, factor the soil pressure, all right? So how do you calculate factored soil pressure? Is easy. So just divided by factored load divided by your initial foundation area. Okay, and this is at 328.2 kilonewton per meter. It's kind of 33 tons per square meter is acting down there. All right, and now let's calculate a shear. Let's start with two-way shear first. Okay, so we assume D as 700 millimeter, and then the effective D, the calculating D is obtained by subtracting, and this is actually H, isn't it? The pile depth divided by the cover and divided by the diameter of one bars, something like this, right? These bars there, and we just come up with a approximate D, effective D, which can be calculated in your design. Okay, and now once you determine a soil pressure, you want to determine entire two-way punching pressure. Punching, it's going to make a big hole around the column at a distance d over 2. All these hatched. Let me check. These are the hatched area. And this is the way your soil pressure is acting to punch out your column at d over 2 from the face of the column. You understand what I'm saying? Okay, this is, not nothing new. If you remember this slab design, okay? right there. So here, shear area, which is the area outside of the critical sections. Okay, and factor not, and you have to multiply the pressure on the area. This is area, isn't it? Okay. So this is the pressure that we calculate. The pressure, I mean the actual load divided by the initial area of the foundation, and this area where you are acting your punching shear is this, and for example, and this is your foundation. This is your column. This is your column actually. Columns here, and this is your effective area. I mean, I think I did. Okay. This is a column, right? So this area is a D column height plus this is d over 2, d over 2, and this is d over 2. What's that? D over 2. So column is the C plus d over 2 times 2 times 2. I'm sorry. This is just the length of this, right? So your square this is the area of this, right? This is simple. Like, all right. So you get this. You get this area, punching area, and loading. So you have a shear. This is called the punching shear. We call this punching shear. You know that, right? It's punching shear. So this is punching shear you calculate, and this is PU. All right, it's factor the punching shear. You can say that. And B0, as we know that B0 is the summation of all four sides here, right? And this is as we calculate 1050 here and times 4 in case for square columns, and B0 the peripheral for critical shear 2A critical shear is 4200 millimeter, and now we're ready to investigate three equations to choose the least, the minimum of them. Okay, here let's say we have, even if we have three equations, we only use two equations. Why? Depending on beta C. So beta C is 1 because we are talking here square columns, so that we don't have to worry about the first equation. We need to take care of second and third equation over there. This is second equations, and this third equations right here. And since we are in center of the foundations, okay, not corner, not edge, so we use 40. This is favorable conditions for foundation in terms of the nominal capacity, shear capacity I told you before, and this is 5434. But we cannot use 5434 as a nominal capacity of the foundation, because the other option, which is third option, gave you a little less capacity than we calculate using equation 2 there. So this is a 2818 kilonewton is the nominal capacity that we have to carry along. It's too bad, isn't it? And we have this is a phi factor right there. And let's take a look at and compare this design capacity to factor the load. Factor the load right there is huge, right? 3658 is way over 2817, right? So it's not good. We're not ready to stop yet. What should we do? We should do something else to increase this capacity. And the easiest way to increase this capacity to overcome the factor the shear force is probably increase your assumed depth to more. Again, we can go to 800. Okay, we can go to 800 from 700, and we have to repeat everything again, but not much. Okay, so the 800 is used to calculate the effective depth. Effective depth is again subtract cover, subtract one bar diameters, And that's what we have as a effectivity to carry along in our all calculations. And B0 also changes, right? Because B0 is a column dimension, column dimension, and add the 1 year, which is 2 of d over 2, which is d, which is now new effective d. Just calculate right here, so that B0 increases a little bit to 4600 millimeters, and also the punching area uh, decreases because your the inside of the critical section increases. Is that correct? So that this is your new factored shear force compared to 3650A. Now we have a little bit decreased VU, which is 3586 kilonewton, right? And again, we are just considering one shear capacity, a design shear capacity right there, and using same equation but different parameters, updated parameters, B0 and D, right there, B0 and D, all of that. So then we calculate what? New design shear capacity, 3600, okay, 3600. And are we okay? Yeah, we are barely okay. We're very close, but you're okay. Nobody can complain about this number, right? Because we have a factored load, and we have a factored load. We have a phi factors are, so we're okay, perfect. And this is good design, right? All right. So now with the 800 depth of foundations, two-way shear has been settled or has been resolved. Now we're ready to go to one-way shear. So one-way shear is is probably okay as long as two-way shears are, since two-way shears are more critical. The one-way shear is also, we have this formula. This is a beam formula. One-way shear is nothing more than you design a beam this directions, right? A critical section B right here from the face of columns, and you're loading acting on this critical section as well. But this is not punching, right? This is a strip loading, linear loading along these directions. So you're calculating VU, which is a factor shear force. So you can take a look at a 30. What is this distance here? And this minus this is at 3 point 3 825, right? Okay, I can see this really. Okay, 825, 825. So 825 times this is what? This is a 825 times. Okay, let's take a look at and calculate the loading on entire foundation, because this is a not infinite running wall foundations, right? So let's take a look at loading on entire foundation, which is 3.5 meter. So this 3.5 meter, and this is a 825 millimeter converted to meters by dividing that by 1000 and multiplying the soil bearing pressure. We calculate in earlier stages, and we get this 1A shear factor, shear acting on 1A critical sections. This is not a punching drill, and this is a calculation for design capacity as a beam theory, and you substitute all the values, properties given in the problem sets, and this beam width and these and all that, right? Okay, this is it. So you're enough. You're enough. All right. So the one issue, as I told you, usually are sufficient as long as your two-way punching shear is avoided. Punching shear failure is avoided. Okay. So you check one-way shear and two-way shear, which are both okay right now after one trial and errors kind of iterations, right? And this is okay. You don't want to use a shear reinforcement, okay? Because the foundation is slabs, and you don't want to use a shear reinforcement in most cases. Most of cases for practical designs, but you want to use a shear reinforcement in beams. But because this is the reason for that, I think is because you have a shallow depth of foundations and slabs compared with that of beam sections. Okay, that's what I'm thinking. And but when you have to, then you can do it. You know, if you have to, then you want to. If you, for example, some residents you cannot have a deeper depth, then you probably you. Anyway, for second very important step is to place a lever. Okay, place a lever. The levers are is not a shear lever, as I say, is a fractional lever. So what do you mean by fractional levers? Are levers to protect the foundation from bending moment. Okay, bending moment. And you wanna just go back again to flashback something. Okay, and the moment is based on entire section of the foundation from the face of the column, as I explained. Here you go. Okay, so the soil pressure for moment calculation is from the face of the columns and all this is like a cantilever, reverse cantilever, right? And you're having a reverse where you expect a, a tension cracks right there. Okay, so the calling back coming back to the sections and okay, you know, okay. Now this is a bending moment at the face of column right there. So this is a span that on that the bearing pressure is acting on, so that this is the bending moment, right? And you calculate bending moment throughout the entire uh, dimensions of the foundation, right? You calculate this, right? And this is a factored bearing pressure, and this is bending moment. Yeah, I don't have to go explain this. And this is a simplified design of concrete sections as a singly reinforced case, and you assume V factor 0.9. JD is the length of moment arms, and you calculate AS, which is lever quantities, and you come up with the 5,600 whatever millimeter, right? So that the minimum, you have minimum lever ratio, the basement for the foundations that we have a 0.18%, so that you have this value as minimum, which is less than what you calculate a minute ago. So you're okay. So and the also you have a maximum spacing requirements. It is 500 millimeter, right? So now your your A values are this. Okay. As I told you already, a phi factor for a fractional member depends on the ductility strength of lever. So this is a brief review on how to determine phi factor, whether it is a tension control and it is in tension control. We can use phi factor. You can use the most favorable conditions. We have most favorable conditions for calculating phi factor. Okay. So now you just go and calculate A as the area and Fy times 0.85 FC an entire section, and A come out to be 39.6 millimeter divided by D. So then now this is enough. We are in tension controlled regions. Okay, so that we can use P factor 0.9. So what is the nominal moment capacity? So we end up with this area which is greater than the minimum values. So we can use a 25 millimeter bars, and here we have a uh, nominal moment capacity can calculate by this value, right? We know everything over there. Okay, and then it is a this value after you multiply phi factor. Okay, all right. So we now end up with a lever that we must place in down phase, but this lever must be placed in two ways: this ways and this ways. Okay, so that's what we explained before. Take a look at. We are going to take a look at whether we have enough developing length of the levers. Developing length, it should go from here to here, right? Okay, and if and we have to subtract the cover from the face of the foundation. So if your lever is not does not have enough developing length in here from here to here, then you have to make another measurement. For example, you can have a hook so that your foundation lever goes down and goes hook, or something else, right? You have to extend the other sides of the foundations unless you have enough developing length. So let's calculate a developing length. And for those who are not familiar with this, you should go back to your concrete design on the graduate review. And LD for tensile lever, this is a given a simplified developing length formula, and dV diameters. And if you have uncoated lever, we don't have uncoated. We don't have coated reinforcement in general. You can use one over there, and the lambda as one again if you use a normal weight concrete, not lightweight, normal weight, right? This is one, this is one, this is diameter. So you need to have at least LD as a 1431 millimeter, which is the minimum developing length, so that your lever here placed in both the X Y direction provides the design moment capacity without slipping out from the concrete section. Right. This is how we have bonding between concrete and lever, by providing LD. Okay, this is one of the easiest and very important calculations. You should go back to concrete books to understand this. Okay? So, and let's calculate how much bar can be extended between here and here, right? This is a 1525 from the face of columns, and I told you that we have to subtract a cover from the face of the foundation to the end of the lever, right? So I'm gonna see if I can write some here without messing up. You're going lever right here, all the way lever. So let's take a look. Drawing one lever here, and I'm gonna erase it. Okay, yeah, your lever stops here because you have a here cover, right? And your distance from here to here is this. Is this. Is this. So this 1450 millimeter is what you can extend in your design. This. Okay. If this distance is less than what you calculate as LD, it's a minimum developing length, then you have some trouble because this lever is gonna slip out of concrete, right? Slip out of concrete. So you can provide a design moment capacity you need to provide to resist affected moment. And that's a serious problem. You choose something else, as I told you, and then you may have a hooked lever like that, okay, like that. If you don't have enough the bar length for developing length you calculate right there. But fortunately, this is 1450, this is 1431, so you are okay. So you don't have to do this. You just go in and get a sections with the straight bars, right? Straight bars. Because you have here length, you have length here. Okay. I'm having hard time with drawings, from here to here, and these are the cover, and you have enough extend the lever length, which is greater than what you have to have for developing length, which is LB over there, right? So conclusion of this lecture for this particular foundation is that you can use a number 11, number 25 lever in both direction, each way, without hook, just normal thread bar, okay? And that's the consequences of the bending moment, fractional design. And you have two shear designs for both a two-way shear and one-way shear, okay?